And next up is Thomas Prellberg.
Yes, hello, let me try to share my screen. Let's see how this works. It's so nice to see everybody, even if remotely, I must say. It's just very pleasant to be here. So I hope people can see my screen now. Is this right?
Yep, all looks good.
Good. I see some affirmative nods. Wonderful. Right. So when I received the invitation request query to present a talk, I really was not sure what I should talk about. I wanted something that was close to Richard's interests, something that kind of touched upon our joint work. And I hadn't done any work with Richard in a while at that point. And then I kind of vaguely remembered that there was this one little nagging open question left from when we did some work in 92, 93 on staircase polygons. So I thought, oh, let me just revisit this and do a tiny bit now. Now, 30 years later, I should be smart enough to do something there. And to just make a long story short, then after I put the abstract on the internet, I got an email from Mireille pretty much telling me that she'd done this, I think, during her PhD thesis. So I didn't really want to change the open question because there's an angle here that I think was open. But I'll tell you a bit more about this in some detail. And of course, it's very fitting that I'm giving a talk right after Mireille gave this wonderful bird's eye view of classifying a whole slew of combinatorial problems, whereas I seem to be the frog hopping around from one little problem to the next one. And there's this particular example of mine. So this is not moving. What's going on here? Here we go. So after the mathematics, there is now the physics introduction, so to speak. So the motivation we looked at here was really about modeling biological vesicles. And you can think of these things as formed of lipid bilayers in a watery solvent. So you have these long tails that don't like the water and the heads that like the water, and then self-arrange to form these membranes that can enclose a volume. And wouldn't it be nice to do some mathematics about this? You can produce these things, these vesicles. They're not a figment of imagination by any means. And of course, you can have more and more structure on them. To some extent, red blood cells, platelets are vesicles as well, if you wish. But let's just stay with very, very simple models, make things two-dimensional. And then you come to a relatively simple model. And it's nice to see Stu Whittington here in the audience as well as Tony Goodman, the Fisher-Goodman-Whittington vesicle model, which basically just says we have a two-dimensional polygon with a perimeter and an area. And can we do anything about this? Can we count these objects? Is there anything we can say? Explicit formulas, generating functions, asymptotic information, whatever there might be. Now, this is a very hard problem. So when you encounter a very hard problem, you always look at simpler cases you might want to study. But let me just quickly explain to you what the actual issue is, and now cross over also to some extent to the mathematical formulation. We're interested in basically looking at counting numbers. These numbers C sub NA, which count the number of self-ordering polygon configuration with fixed perimeter on the square that is always even. So we mod that out, and fixed area A. And we multiply this then with generating variables T and Q, and sum it all up over all possible values of N and A, and that gives us a generating function or a partition function or whatever you would like to call this, depending on the background that you have. And then it turns out that you can look at the singularity structure of these things. of these generating functions, and the closest singularity of the origin in these a large class of these models has got this particular structure that you have a transition between different phases. You have an inflated phase where the vesicle is essentially blown up and round with a large internal area. And you have another phase where you basically have a seaweed-like area where things pretty much look like branched polymer. So the vesicle maximizes perimeter and tries to minimize area. And if you are a physicist, you get very interested in these things because there's a phase diagram in this model. You have a critical point, tricritical point details, and you can define critical exponents that tell you something about the singularity structure, how the singularity of the generating function behaves in the vicinity of this critical point. So this is all very interesting, and this is sort of the motivation that you come to when you come at this from the statistical mechanics point of view. Now, I don't really want to talk about many of these things, but I just want to set up this field because I wanted to now talk a bit about the relevant work that I was part of when I was a postdoc in Melbourne with Richard and Tony. So we actually did quite a bit. Richard was at that point still somewhat more of a physicist, I suppose. We did do quite a bit in terms of looking at the scaling behavior of these models by writing down a whole scaling theory, somewhat conjectural in some aspects. However, we moved very, very quickly also to companion papers on exactly solvable models where we couldn't do the whole thing in the full discrete case, but you could define a semi-continuous version where one of the lattice directions was modified to actually become a continuous variable. And in that case, we could make some headway and actually computed quite a bit of things. And therefore, we could actually get the scaling behavior of these vesicles as well. And then if you take the discrete model seriously, you end up with something that gives you cutiform functional equations in general. And that is this one paper that I very much like from that time, where we could push this to actually get from those functional equations, Q-algebraic functional equations in this case, even the critical exponents from these models. So we had a fair bit of idea now about the behavior, about the critical point. We managed to actually pin down these exponents indicated in this picture here. And then in the summer, I believe everybody went away to Europe, and I stayed behind in Australia. And so there's this one single author paper that I would like to mention. By pure accident, it's a single author paper because nobody else was there to talk to. And that's where I actually managed to nail down the full scaling functions for one of these models, namely staircase polygons. And these staircase polygons now form the basis for the rest of the talk, really. But just to point out why I liked this paper quite a lot, and I guess why Richard might have liked it quite a lot as well, is if you look at the citation details of Richard Brak on Scopus, you find that this is actually his most highly cited paper with 85 citations, which I wasn't even quite aware of that it had so many citations. But in preparing this talk, I looked at this, and it actually pleased me to see that there was a relatively high number coming up here. So having said this, there is a different strand of work done in the French school. And there it turns out that similar problems have been studied around the same time. One could say a tiny bit earlier. And there's a paper by Mireille and Xavier Venot from 92 that actually very much covers very similar ground. And I'm somewhat ashamed to say that we first cited this paper explicitly in our work in 1999, so a lot later than we possibly should have. We just simply, I believe, weren't quite aware of these contents. It was the Journal of Physics A audience versus the Journal of Combinatorial Theory A audience, I suppose. Plus, this paper was written in French, so it's a bit of a threshold sometimes. So back to what we were looking at, what I want to talk about now, staircase polygons. It's a particularly simple model in this whole set of simple polygon models. And this is a picture from our paper, from the one with Richard, and I've encircled the one of staircase polygons, also sometimes known skew-Ferris diagrams or parallelogram polyominoes, and I'm sure there's other words for it. And this is the one I want to just briefly look at. And first of all, if you're interested in the generating function for this one, here it is. It looks quite nasty, but you can do lots of good mathematics from it. And here I would just like to point out that you have a ratio of 2 infinite series, and the only distinction here is really that there's an extra factor q in the numerator that doesn't appear there in the denominator. So these sums are actually q-Bessel functions, and I don't want to dwell too much in the q-series notation, so I will try to avoid most of these things here. The one thing I want to point out is at that point, Richard and I had a discussion, and we basically realized we could only do this by differentiating horizontal and vertical perimeter. And we could only do this by writing down a generating function expression that did not reflect the symmetry in x and y. Naturally, if you look at the picture here, this model, if you flip it across along the diagonal axis, must be symmetric, but this expression definitely was not. I was more keen to rush on to other things and do something with this expression, but Richard was kind of nagging me, and at some point I think gave up to ask me to do something about the asymmetry here. But how did we get to this exact solution? I want to briefly talk about this because that will sort of tell you how one can actually tackle the symmetric version of this that I will describe later on. So there's lots of ways of finding these solutions. You can use bijections to other objects. So you can, for example, map things to Q extensions of algebraic languages. You can map things to Dick paths. You have all sorts of ways of actually mapping these objects to other known objects and then pull over the results that are known to say something about these staircase polygons. One very clear way of doing it is to use the theory of heaps of pieces. And for those of you that know what heaps of pieces are and know how they appear in generating function, the given expression from the previous slide already tells you there should be heaps of pieces theory here because of the particular way this ratio here appears. I don't want to say more about this at this point. That would be a whole different talk. I would rather dwell now more on combinatorial decompositions leading to recurrences of functional equations. This is basically the work that Richard and I were doing at that point as well. So if I now just briefly drop some arguments here, you can decompose staircase polygons by just looking at where the neighboring columns only have an overlap of 1. And if you look at what this means, it really means that you can decompose the set of all staircase polygons to staircase polygons that are, this little bar means that the height is increased by 1. And then you can join another staircase polygon to the set of those that have heights increased by 1. And if you look at what's missing when you look at these two sets, then you see that the single square is missing, and the one where you have a little square at the beginning of a staircase polygon. So these rectangles here are staircase polygons. They're just drawn in the simplified fashion. I think back then we were doing picture drawing with LaTeX, from what I remember. So it was very painful to do these things beautifully. So this is again a picture from our old paper then. So you have a functional equation now, because all of these things transfer right away to the functional equation, to the generating function language, because increasing the area in each column by 1 means you just multiply every variable x by a q, for example. And you can explain the other terms in a very similar way. Here you increase the vertical parameter by 1, so you get a factor of y. Here you have increased it by 1, but then you glue things together. That means you remove this factor of y again, and so forth. So now for the slight bit of magic, and this is something that we managed to do in Melbourne. This functional equation here, which is nonlinear, you can, if you stare at this long enough, you see it, it's kind of akin to a Q version of a Riccati equation. And a Riccati differential equation has got a linearizing ansatz. And the analogon here is actually to find an ansatz like this. And if you just plug it in, and just believe me, this works, you'll see it works, you see that this ansatz here turns a nonlinear equation to something linear, and linear is always a lot simpler. So in this particular case, all you have to do now is to insert a series expansion in X, which immediately gives you a nice recurrence expressing Tn in terms of Tn minus 1. And as they like to say in London, and Bob's your uncle. So you can finish things all off by iterating this recurrence, and you're finished. And you get the expression from the previous slide. So now the hope would be that one could actually do this for the symmetric case. So again, Richard was bothered that we did not use the symmetry. If you mess about just purely algebraically with the original functional equation, use the symmetry that you know exists, you can write down a functional equation for the that is symmetric in X and Y. You see here, you basically end up with a Qx and Qy back here, and these terms all are nicely, this equation is symmetric on the exchange of X and Y. Can we understand this? And the answer is, of course, yes, we can. There is a corresponding combinatorial decomposition, which you can do by just using this wasp-based decomposition along the diagonal of the staircase polygon. It's actually almost a bit nicer than the original equation, because you sort of see it's a single square or a single square prepended to a staircase polygon either below or above. Or here is one where you simply inflate one of these staircase polygons and glue a non-inflated one together with this. And if you just look at these 4 terms, that correspond exactly to those 4 terms down here. So this looks very nice, but we did not bother solving it back then. When I say we did not bother, what I remember is I tried and I couldn't do it, or I wasn't patient enough, or something of that sort. This was 30 years ago. My memory fails me a bit about those details, but we did not do it. So let me just see now with a bit more wisdom what I can actually do if I put my head to it. And this is actually what I was trying to do over Christmas when I was looking at this again. And I was trying to see if we could close this gap actually. So I'm just changing the notation slightly by introducing a generating variable t in the appropriate way, and the functional equation becomes this one here. It's a nonlinear functional equation. It is very similar to the one we've just done before. Let's look for a linearization ansatz. And After a bit of thinking, we find one. This one works. It linearizes the functional equation. So far, so good. We should be in business, one would think. But now the issue is if we do the same kind of ansatz, series expansion, and I have to say I've already presciently added a prefactor here to the UN to make the following equation a bit easier. You see you get not a simple recurrence, but you get a two-term recurrence equation. And that makes life a lot harder, especially because there's this factor q to the n still floating about here. But we can do these things in principle. So let's just plow through with these things and do them in principle. It's harder to solve, but actually turns out if you really put your heart to it, not that hard. You kind of can see that this equation here has the left-hand side, which is a nice recurrence with constant coefficient, and the right-hand side is something else. But you have a characteristic polynomial involving minus x or minus y as eigenvalues, and this power on the right-hand side suggests now an expansion of the UNs in powers of q to the m. So let's write down a different series expansion now with coefficients v. And it turns out that this recurrence can in fact be solved by iteration. And you see there's an initial condition here which involves the characteristic polynomial, and therefore you have minus x or minus y as values for lambda that you need to specify. So we have now two linearly independent solutions here in terms of these u lambdas that we get by iteration. And we have to specify lambda equals minus x or lambda equals minus y. And now we still need to satisfy the actual initial conditions of the recurrence. We have some arbitrary overall factor. So in principle, we only have one condition we have to worry about that fixes the ratio between the prefactors a and b. And that would be our solution. Well, let's put it all together. Find a and b, substitute back, put it all together into the full answer, and we get a result that is as follows. S of x, y, and q, our generating function has this structure here where u has an explicit expression of this type. It looks horrible in my mind. I mean, there is an explicit symmetry in x and y, but that's all I can say in favor of this. And now it turns out that I got this email from Mireille reminding me that she'd done this in Lemma 4.5 in a work in 1992 with Xavier. And in fact, if you just look very carefully, there is a functional equation in there that is exactly the same functional equation that I had just been playing with. And it turns out that there is not just this very complicated, awful-looking solution, but a much more compact solution that, because the solution to this, the regular solution, it's unique. These two solutions have to be, in fact, identical. However, I haven't bothered showing this explicitly. Possibly interesting as a side comment is that their paper arrived at this generating function structure bijectively, coming from heaps of pieces, I believe, and then wrote down that the generating function here, that this part of the generating function actually satisfies the following functional equation. And I've just done it the other way around. I had the functional equation, was trying to find a solution, and that was the best I could come up with. So I still would like to know if they actually try to solve this functional equation directly, but presumably they didn't have to because they had the solution already in front of them. But The other thing is it pays off to be able to read French language papers. Mireille was mentioning at the beginning she had issues with English when she started off. I had and still have issues with French, so there was a certain language barrier to get past as well, looking at these things. These days I feel like I understand her papers quite well, but back then I guess I didn't. So to put it all together, the solution to this equation is given by either this or that, and I can confirm that these two expressions here, connected by the equal sign, are in fact both correct and identical. I just don't have the appetite for showing that explicitly. Okay, so I think my time's roughly up. I would just like to summarize that. Not quite sure how I should summarize this. I've submitted lots of nice pictures with Richard. I could talk more about Richard, but I'm sure other people are doing this, and we're all missing him terribly. And it's somewhat cathartic to be here to be able to give this the talk. So this has very much been a back-looking, reminiscing talk than a forward-looking one. I've, to some extent, really restricted myself in this presentation here and in this little piece of work that I did over the Christmas break. Two techniques that I actually learned while I was a postdoc in Melbourne. And all I can say in closing is that Richard has really shaped my career quite tremendously. I still dabble in all these things that I encountered while working in Melbourne with him. And I think I will continue to do so. And with that, I would like to close. Thank you.
Thanks very much, Thomas. Anybody online who'd like to ask a question? Yep, Gary.
You need to unmute yourself if you.
That was just a clap.
I was just clapping at a job well done, and great to see you, Thomas.
Anybody else? No? Any questions in here? No? All right, it was all perfectly clear, Thomas. Okay, we are pushed a little bit for time, so maybe let's thank Thomas one more time.